Hello, students. ¿Cómo está usted? ¿Dónde está usted? Hey, we have a customer. Stuart. Good going, Stuart. So far we have Stuart. And I want to see a picture of this whiteboard. How do I, oh, there we go. Stuart, how are you today?
Doing all right.
Hey, good deal.
I just sent you an email. I accidentally submitted my Unit 2 Assignment 3 into
Yeah,
the Dropbox for Assignment 4. So I
yeah.
emailed you Assignment 4.
Oh, we'll figure it out, Stuart. I guess if worse came to worse, you could send it to me on the email rather than the what do they call it? Blackboard. Let me look at your what's missing on your homework scores here, Stuart. Stuart. Stuart, you're not missing anything. You're not missing a thing according to my records. So I don't know. I guess you're okay. Now you didn't. Just between you and me, nobody else is on there. You didn't get a 4 on your last thing, but I usually write a little note there why. I think some of you guys are forgetting to sketch the process on a PV diagram. And if you don't do that, you don't get a 4. That's just the way it works. Well, let's see if anybody else is showing up here. Let's see. Nope. Stuart, it's just you and me right now. Have anything else to say, Stuart? Stuart doesn't have anything else to say right now. Okay. Well, we're early. We got another 6 minutes or so. I think I'm going to go get my another calculator. You know how these calculators are. They just right in the middle of something important, they quit working. So I'll be right back. Get another calculator. All right. Well, Stuart, it's just you and me. I think we're going to have a one-on-one class, looks like. Did you have any other comments or questions? Well, I guess we'll just wait till we have 3 minutes and then our class will start. I guess it's officially summer now, isn't it? And yeah, I think the 21st or 22nd was the first day of summer. They call it the summer solstice. Yeah. So we're into summer now. Stuart, say something.
Something.
Well, what is your major? What are you going to do? What's your major?
Mechanical engineering.
Yeah, good. Now, are you going to go to OSU?
Yes.
Great. Have you had strength of materials yet?
I am taking it this semester.
Oh, you're taking it. You mean this summer? You're taking it this summer?
Yes.
Ah. Well, have you had elementary dynamics yet?
No. I'll do that in the fall.
Hey, I know a really, really good instructor that teaches that this fall. Are you going to take it at TCC?
Yes, I'm taking it at TCC.
Yeah, well, that's what I mean. I know a really good instructor that teaches that at TCC this fall. Are you interested?
Sure.
Well, it's me. I'm not real sure how it's going to work, though. It's possible it might be blended, part online and part face-to-face. I don't know. We'll do what the bosses say. Okay, I need to make that. Yeah, there we go. Well, I got 8:30. Well, what do you guys have? I've got 8:30. It's time to. Hey, we have another customer, Spencer. Say hello, Spencer.
Hello, good morning.
Yeah, good morning. Spencer, what time do you have? I have 8:30. What time do you have?
I'm showing 8:30.
Yeah. Well, I think we should get started unless you guys have a question for me. We're going to start on our topic, which will be cycles. We're studying cycles today.
I do have one question.
Go ahead.
So, I received your email yesterday because I asked you on Monday about the homework assignment that was supposed to be due on Monday but wasn't posted anywhere on Blackboard.
Really?
So, like at least myself and Parker were unable to even access it, so we didn't know what questions we were supposed to be doing. And even if we did, there was no submission link, so we couldn't turn in the homework.
Well, that
I was just wondering if you'd gotten that issue resolved.
That could have been entirely my fault. I'm talking to Spencer, right?
Yes, sir.
Yeah, Spencer, that could have been entirely my fault, and so I should not penalize you guys for that at all. Was it 4:30 and 4:26? Is that what it was, you think?
Yes, that's what you told me yesterday in an email.
Yeah, I think I guess do those and send them to me on my email.
Okay.
And I have no idea what happened. I'm hoping that nothing else is all screwed up.
The assignment for tonight is up there, so I'm not. I think it was just a one-time thing.
Oh, I hope so.
And when do you need those by? 4:26 and 4:30.
Well, because if I screwed up, I guess I'll just have to not worry about it too much. Do it when you can, okay?
All right.
Thank you for letting me know about that. And you weren't the only one. There was somebody else that had the same trouble.
I know at least Parker having the same issue. I
Yeah.
can't vouch for anybody else, but I know at least Parker was having the same issue around noon on Monday.
Right. Well, do that and we'll figure it out. Okay, well, unless there's something else, we're going to jump into this topic about cycles here. Now, this is a new chapter, though, isn't it? Yeah, I think this is chapter, I believe it's chapter 5. Is that right? Let me look and see here. Chapter 5. Yeah, I think it's chapter 5. Okay. Well, let me jump into that. Now, the title of the chapter is not cycles. It's the title of chapter 5 is the second law of thermodynamics. That's the title. Trying to find, yeah, here we go. The second law of thermodynamics. Okay, well, we'll mention that too, but really this chapter is about cycles. And here they are. There's the power cycle. Now the power cycle has another name. It's also called the heat engine. Means the same thing. And then there's the refrigeration cycle. And there's the heat pump cycle. And finally, there's the Carnot cycle. Now, the Carnot cycle is just a particular version of the power cycle. It's a very special power cycle. So that's what we're going to study. And the first topic is the power cycle. Now, first of all, what is a cycle? Well, a cycle, you've studied processes. Like on a PV diagram, you've studied processes like from 1 to 2. There you go. That's a process. Well, see, if you could go from 2 to 3 maybe, and then go back from 3 back to 1, well, you'd have 3 processes, but you'd have a cycle. You come back to where you started. That's all a cycle is. Not now. It might have 4. It might have 4 processes. Look at here. You could go from 3 to 4, and then you could go 4 back to 1. Or you could have 5 processes or a dozen, whatever. It could have as many as just 2. Look here. If you went from 1 to 2, and then you went from 2 back to 1 like that, well, that's a cycle. It's a cycle, isn't it? So that's what a cycle is. Now, power cycles, you'll discover when we study them, are clockwise. Did you notice this here is clockwise? But refrigeration cycles and heat pump cycles, both of these are counterclockwise. So just reverse the, here, we'll do some counterclockwise stuff here. Here we go, 1 to 2, 2 to 3, 3 back to 1. Look, I went counterclockwise. Now, a Carnot cycle, it's a power cycle, so it would be clockwise on a PV diagram. So that's that. Any comments or questions before we talk about the power cycle in detail? Okay, no, I don't hear any questions. Okay, well, let's talk about the power cycle. Now, they draw these in your book. Let's see if I can find one. Yeah, I see one right here. They have a heat engine, and they drew a cycle. I'm on page 145. We're going to talk about power cycles now. And well, they put in a boiler. And then they have a turbine. We studied turbines a little bit. And then they have a condenser. And see, we're going around here clockwise. And then they have a pump. And notice it's clockwise, and it would be clockwise on a PV diagram. Now they have the pump connected to the turbine. Well, that's what powers the pump. I guess you could have a pump that was powered by electricity. Doesn't have to be powered by the turbine, but on that page there, I happen to be on page 145. They have their pump powered by the turbine. Now they have some heat exchanges going on. They have a heat transfer into the boiler. There it is. They call it QH. They put a dot over it. That means it's a heat transfer rate. And then the condenser, see, it has a heat transfer out. They're going to call that QL dot. The L stands for low temperature, the H stands for high temperature. And the condenser is transferring heat to the environment. But the boiler the environment is transferring heat to the boiler. You know, you're burning coal maybe, or oil perhaps. You've got some kind of power source or you're burning wood or something. So we're talking about heat engines, and you kind of understand that now. Now there's a W dot right here. That's your power. It's a power cycle, and that W dot stands for power. Okay, makes sense. Now these heat engines or power cycles have an efficiency. Let's talk about the efficiency. They use a Greek letter eta. That is the Greek letter eta. Let's see. Alpha, beta, gamma, delta, zeta, eta. There you go. Theta, iota, kappa, lambda, mu, z, omicron, pi, tau, epsilon, phi, chi, psi, omega. Well, eta is a Greek letter, and it stands for efficiency. Now, efficiency is always a quotient. It's something that you want or desire. It's something that you desire divided by cost. So it costs you something. Now, like, did you know that some students are more efficient than others? See, the desire is to get an A, right? Get a good grade. And the cost is you got to spend a lot of time thinking about this stuff and doing problems for Mr. Griffin and erasing the stuff that you messed up on and starting all over. And it just takes time and effort. This is the cost. But did you know some students they get high grades and they don't seem to have to work very hard. Others, normal people like myself, I can get a high grade, but it requires a lot of time and a lot of work, which is okay. There's nothing wrong with people that have to work for what they get. But that's what efficiency is. But what is it in terms of a heat engine? Well, I have a schematic that's a little different than theirs. They have another type of schematic here. Let me show you that. See, this here kind of explains a heat engine. Guys, the topic right now, if you just tuned in, is the heat engine. That's what we're talking about, heat engines. And another name for it is the power cycle. It's the power cycle. And they had this particular version on page 145, and they have another way of expressing it in your book. Let me show you that way. Then I'm going to show you the way I want you to do it. The topic today, right at the moment, is heat engines or power cycles. They mean the same thing. Now on page 150, they've got You got a thing like this. So you got the high temperature. No, wrong one. Wrong one. Just a minute. Wrong one. Let me find the right one. Yeah, here we go. Well, no, I still don't see what I'm looking for. This will work. This is on page 162. They've got a TH, that's the high temperature. And then they have a QH dot. And then they have kind of a goofy looking thing that looks like this. And then they have a QH, a QL dot, and a TL. This is on page 162. And it's another way of expressing a power cycle. But now I'm going to show you the way I want you to do it. And I call this my cycle schematic. That's a cycle schematic. And I had another one that I erased a minute ago. But here's how I want you guys to do it. You're going to have a TH, high temperature, a QH dot, heat transfer rate from the high temperature, and you're going to have a clockwise, around and around clockwise cycle, and then you'll have a QL dot and a low temperature TL, and then coming out here you'll have your W dot, that's your power. This is the way I want you to do the power cycle schematic the Griffin way. You know, it's all the same. And now let's write the efficiency. Well, what you want is this W dot. That's why you have power cycles, to provide you with power. And then you have to divide by what costs you. This usually is in terms of money, okay? We're usually talking about money. And see that QH dot, you got to pay for that. Like if you have a lawnmower, you know where you get this heat transfer from? You get it from burning gasoline in your lawnmower, and that you have to pay for that gasoline. So that costs you money. And in this, for a lawnmower, it would be the power of cutting your grass. So that's the efficiency of your lawnmower. Now, for the first law of thermodynamics, this numerator is equal to QH dot minus QL dot. So you could write this, you could write that efficiency like that. See, here, let me give you some numbers. So suppose this was 20 kilowatts, and this was 12 kilowatts. Well, then this would have to be 8 kilowatts. See, the first law of thermodynamics says if you have 20 kilowatts coming into your cycle, this is your cycle, and you get 12 kilowatts of power out of it, well, then you're going to have 8 kilowatts. Some people call it waste heat. For a lawnmower, what that is this hot exhaust. See, you did not buy that lawnmower in order to have some hot exhaust coming out of it. You bought it to cut your grass. but every heat engine has a heat transfer to the lower temperature. This lower temperature would just be the atmospheric temperature. Next time you run your lawnmower, if you have a gasoline lawnmower, put your hand about, I don't know, 6 inches from the exhaust. And when it goes chugga chugga puff puff, chugga chugga puff puff, you'll feel hot exhaust coming out of there. Well, that's what this is. This is your heat transfer to the environment. You're heating up Oklahoma when you run your lawnmower. Okay, and this is what I call the actual efficiency of your heat engine. Now there's another equation, and they have different names for it. This is your maximum possible, I guess is one way of putting it. They have numerous names. Another one is the efficiency if it's reversible. And we'll be talking about reversibility. Another name for this is the Carnot efficiency. If this thing could run perfectly with no friction, for example. See, friction, that's where they have oil in your engine, is to reduce friction, right? See, the friction cuts down on your efficiency. You don't get as much power because you're using some of that power to overcome friction. And what this is the maximum theoretically possible efficiency that you could ever get with your power cycle. And it has an equation, and it goes like this. If you could learn this one here just involves the Kelvin temperatures. But keep in mind, these have got to be Kelvin, or if you're in English, they have to be Rankine. So there's your equations, and those equations are at the end of chapter 5. Let me see if I can show you. You could look them up. I'm trying to find them here. Well, it's a little bit subtle, but they're there. They're kind of in disguise, but they are there. They write them a little bit differently. In the back of your book, the way they write this one is a little room here. Not the back of your book, the back of your chapter. At the end of your chapter, they write this one as 1 minus QL. They just took the dots off. I think you can find that equation there in the back of your chapter. And I'm on page 171. And this one, they write that as 1, it's just an algebra thing. I bet you can get from here to here, can't you? They write it, keep in mind though, it's got to be absolute temperatures. Well, there you have your equations. And we're going to move on to the refrigeration cycle. There's several cycles we're studying today. The first one is the power cycle, which is also called the heat engine. And the next one is the refrigeration cycle. But before we move on, better yet, let's do an example of this. We'll do an example, and then we'll move on to the refrigeration cycle. But before we do that, did anyone have a comment or question? Comment or question? Okay, let me see who's on board here. Just curious. Oh, we got a good crowd. Look, Stuart and Spencer, Parker, Bear, and Aubrey. Well, that's a good crowd. Well, let me put them down in my folder here. Now let's see. We've got Parker and Stuart, Bear, Aubrey, and Spencer. Maybe the others will show up, but we do have these on YouTube for you people that like to sleep in. I guess you could watch it on YouTube. All right. Before I do an example, you could also do this with little letters. You could go 1 minus little ql over little qh. There's no little letters on this one. But see, you have little letters, you have big letters, and you have big letters with a dot over them per time, okay? Okay, well, here's what I wanted to do. I wanted to do an example. This is problem 514. Problem 514 in your book. So let me make some room here. And the topic is the power cycle, which is a type of heat engine. Okay, now let me read it and see what it says here. Power cycle 514. Okay. It says a large coal-fired power plant has an efficiency of 45%. All right. Now, what they're talking about is the actual efficiency. They're not talking about the theoretical maximum. They're talking about the actual efficiency. And it produces a net 1,500 megawatts of electricity. Well, I think that's either going to be big W dot, or little w. We'll figure out which one it is here in just a minute. But they said it's 1,500 megawatts. Okay, now I'm going to go to one of my excellent students. You got a 33 1/3% chance of getting this right. I'm always picking on Stuart. Stuart, this 1,500 megawatts in problem 514 says the power plant produces a net 1,500 megawatts of electricity. Stuart, is that a big W dot, or a little w? What do you think, Stuart?
I'm gonna say big W.
Big W. You got another guess, Stuart. I tell you, big W. What that would be megajoules, for instance. Okay. See, joules is not in. Watts is different than joules. See, W is in joules. Watts is not in joules. So what you got? You're down to, you got a 50-50 chance of getting this right, Stuart. Go for it. What do you think?
I'm gonna go with little w.
Stuart, it's like playing roulette, and you just lost. Stay away from the casino, Stuart. Watts is in big W dot. See, that's per time. See, a watt, let me tell you what a watt is. A watt is a joule per second. That's what a watt is. And what's confusing is W stands for watts. W stands for watts, and what that is am I doing that right? Yeah, I think so. See, watts is in no. I don't want to tell you the wrong thing, I'll get in trouble. See, watts is W dot, and W is in joules. And see, a watt is a joule per second. Now, if you want a kilowatt, you don't put it there though. If you want a kilowatt, then you have to put a K in front of it. But this is a megawatt. I've probably totally confused everybody. But I'll tell you this, that 1500 megawatts is a big W dot is what it is. So let me write that down for you. We have to know what this stuff is. What's so confusing about these watts is they have a W for work, that stands for work. They have a W dot, that stands for power. They have a little w, that stands for work per mass. And now the units, see, these are not units. These things are symbols. And these things are names. And now the units for work, you could be kilojoules, for instance, or megajoules, or just joules. That'd be all right. And I put those in brackets so I don't confuse myself. Stuff is confusing enough already. Power is in watts, or you could have kilowatts, or you could have megawatts. See, that's megawatts. I should have put it in brackets. Now, little w is work per mass, and that's in joules per kilogram. Or you could have kilojoules per kilogram, or you could have megajoules per kilogram. See, these are units, these are names, and these are symbols. Notice I don't put symbols in brackets. You'll never see me put a bracket around that W dot because that's not a unit, it's a symbol. Okay, well, we got that. I hope you understood it. Let's keep going. Now we're doing problem 514. Can I erase that? I know you guys diligently copy down everything I put on this board and study it diligently, don't you? All right. Well, let's keep studying here and reading. I'm doing problem 514. In my book, it's on page P41. I guess P stands for problems. A large coal-fired plant has efficiency of 45%, produces a net 1,500 megawatts of electricity. Coal releases 25,000 kilojoules per kilogram. as it burns. Well, now we got to figure out what the heck that is. Again, I'll pick on somebody besides Stuart this time. That there is either a big W or a big W dot or a little w, or I guess you could have little w dot. That's possible. Let's go to my friend Spencer. Spencer, you have a 25% chance of getting this right. That 25,000 kilojoules per kilogram. Spencer, which is it? Is it the, see these are the symbols here. Well, which one do you think, Spencer?
Little w without a dot.
Little w without a dot. You know what? You're right. Only where I'm screwing up here is I think this is a heat transfer. So I should have written this. We're not dealing with W's here. We are dealing with Q's. But I think Spencer said this one here, didn't you?
Yes, sir.
Yeah.
Third one down.
Third one down. That's it. That's what that is. Good going. It can be, see, I can get confused too. But we just figured out that this here is little q. I think, or is it little w? Let me think now, let's see. Yeah, when it talks about burning fuel, they're talking about a heat transfer, aren't they? It's heat transfer per mass. Sometimes the book calls that specific heat transfer, which is okay with me. I would call it heat transfer per mass. That's what I would call it. See, there's the symbol, that's the name, and well, that's the amount, and that's the unit. The book calls it specific heat transfer. That little q, the book calls it specific heat transfer. Now that's different than specific heat. Specific heat is an entirely different thing. Has different units. Okay, well, we're doing great. So we got all that. Now we're going to draw our we're going to draw our schematic. All right, here goes. There's some room over here. Now remember, this goes clockwise because it's a heat engine. And in this case here, I think we want the little letters. I get the feeling we want the little letters. Okay, now there's our clockwise schematic. I call this the cycle schematic. That's what I call it. It's a little different than the way the book does it. And if you'll do it the way I do it, you'll make me happy. All right, now do we have all the info? Let's see. Yeah, I think so. All right. Well, we don't know the temperatures, so we can't get those. They never gave it to us on this problem, did they? So forget the temperatures. But we do have an equation for this. The way it works is you would have QH minus QL over QH. Well, now, which is this? Is this QH or QL? I think that's the QH. That's the burning stuff. That's not the exhaust. So look at here. They give us that. We know it. So, hey, we could solve for the little QL, couldn't we? See, this here is 25,000 kilojoules per kilogram. We just have an algebra problem. Now I'm going to do that algebra. And I want you to do it too. So I'm going to shut up for about a minute and a half. And I want you to, can you see my equation here? 0.45 equals this here. All right, go for it. Solve that. Well, I got an answer for QL. Did anybody out there get 13,750 kilojoules per kilogram when they solved this equation right here? I think that's right. Let me double check it. Yeah, that looks right. So so how much work per mass or per yeah, how much work per mass do you get? I wonder, is that what they want to know? What do they want to know anyway? So how much goes? Oh, okay. Here's what I think they want us to do. See, W dot is equal to M dot times little w. And we can get little w because if you have 25,000 coming in and 13,000 going out, well, what do you got here? Just subtract, see what you get. 25 minus 13.75. Do you get 11,250 kilojoules per kilogram work per mass? Output. I think that's right. Okay. So look at here. We know this. And we know this. Here, let me write it down. This here's 1,500 megawatts. We're trying to solve for the mass flow rate. And I'm thinking this little w is 11,250 kilojoules per kilogram. So we're going to solve for M dot now. Go ahead. Go ahead and do that. Well, I got an answer. I'm kind of running out of space here. There's a little space here in the bottom. I'm getting a mass flow rate of 133 kilograms per second. And I wonder if yeah, that's right. Only if you read the problem, they want it per hour. Well, there's a little room up here. We can get it per hour. If you have 133 kilograms per second and you want it per hour, what you do is you go 3,600 seconds is equal to an hour. Isn't that right? 3,600 seconds in an hour? Okay, well then you multiply that. Isn't that what you do? Yeah, because see, the seconds will cancel. All right. So we'll take the 133 and we'll multiply by 3,600. Gee, I get a humongous number. I get 478,800 kilograms per hour. Wonder if that's right. Let me look and see. Let me see here. The book has, the answer book has 480,000 kilograms per hour. They are just being lazy. We got 478,800. Just round it off and you'll get what the book got. I got a bad feeling I probably lost a couple of people on that one. What we just did is we just solved problem 514. It's a power cycle. And the way you do these is you draw the schematic and you try to fill in the amounts, and then you have an equation. And it's kind of messy, but there's the equation. And you try to solve it. Does anyone have a question or comment about problem 514? Well, I wish I knew where you guys were on this, if you were totally lost or if you're doing okay. Let me ask somebody. Let's see. I'm going to ask Bear. Bear, did any of that make sense, Bear?
Yes, it did.
Okay, good deal. Well, let's do a refrigeration cycle now. I need this room, so we'll say goodbye to the power cycle for a minute. That was a power cycle. There's what we're doing today is power cycles, refrigeration cycles, heat pump cycles. And then we'll do a Carnot cycle, but it's just a type of power cycle. But there's these three kinds of cycles. But right now we're going to do a refrigeration cycle. That's the topic for right now. It's a refrigeration cycle. And they draw these in the book. In fact, I think one of your homework problems, problem 515, is I believe that's one of your homework problems. Let me look and see. It's a refrigeration cycle, but I don't want to do it because that's your homework. You need to figure this stuff out. Yeah, that's one of, they've got a refrigeration cycle there. Now, what's confusing, it looks like they got it going clockwise on problem 515. They shouldn't have done that. That's really poor. They should have it going counterclockwise. Here, let me show you what they should have drawn on 515. I don't want to do 515 because that's your homework. But they do have a compressor. Now, compressors are kind of like turbines, but they're a little different. And they've got a compressor. And after the compressor, they go to the evaporator. No, they go to the condenser. You got the compressor, and then they go to the condenser. I am looking at on page P41, and then they have a condenser. This is the way they should have drawn the diagram. And then after the condenser, they have a expansion valve. And then after the expansion valve, they have the evaporator. And then they input to the compressor. This is how they should have drawn their diagram on problem 515. Theirs is correct, only it looks like it's going clockwise, doesn't it? If you happen to have that page there. But see, it's on a PV diagram, it'll be counterclockwise. Refrigeration cycles are counterclockwise. Now, here's how I want you to draw the cycle schematic. It goes around and around counterclockwise. Now let me look and see what they're doing on. We are going to do problem 514. I'm going to erase this 515 so I don't get confused. But they've drawn this thing backwards on 515, and I just drew it the way it should. They should have done it, but they didn't. Okay, and if you read 514, they said the efficiency is 45%. No, wait a minute. I don't want to do that one. We just what I want to do is 535. We are going to do a problem. We just did 514. We are going to do what did I just say? 45? I think that's what I just said. No, 535. we are going to do 535. Now it's a freezer, but a freezer is a type of refrigeration cycle. It operates in a room at 20 degrees Celsius. Well, see, that's this one here. That's the 20 degrees Celsius. Let me keep reading. Heat must be transferred from the cold space at a rate of 2 kilowatts to maintain its temperature minus 20. I'm thinking this temperature is minus 20 degrees Celsius. Now they said you have heat is being transferred from the cold space at a rate of 2 kilowatts. See this right here? This is 2 kilowatts from the cold space. But we got to decide, is that 2 kilowatts? Is that a QL dot? Is it a QL? Is it a little QL or is it a little QL dot? See, these are symbols. I just spell symbol, BOL. Yeah, those are symbols. And see, that's a number and that's a unit. That there is a unit. And they also have names. This here is called a heat transfer rate. That's called a heat transfer. Here, let me write them down. That's a heat transfer rate. This is a heat transfer. This is a heat, you know what this is? It's a heat transfer per mass, per mass. And this little guy here is a heat transfer rate per mass. It's a heat transfer rate per mass. You must know the difference between the names of things, the symbols for things, and the units for things. Now, in this problem here, 535, they told us that you have 2 kilowatts. I got lost here, 535. It says here, heat must be transferred from the cold space at a rate, you know what, that's a heat transfer rate, isn't it? At a rate of 2 kilowatts. So which one of these do we want here? I wonder which one we want. Let me pick on one of my excellent students here. See where we are here. Aubrey, I'm always picking on you. Aubrey, there's a 2 kilowatts here. We got to figure out, is it QL dot, QL, little QL, or little QL dot? Aubrey, what do you think?
It's the big QL with the dot.
Big QL with the dot. Now let me think now. Let me think and think and think. Big QL with a dot. You know, I think she's right. I think she's right. Good going, Aubrey, because see, I think Aubrey's right. I think that's a 2 kilowatts. See, if it was this one here, it wouldn't be watts, it'd be 2 kilojoules. Now this one here would be, I don't know about the 2, but it'd be in kilojoules. Here, let's put the units in brackets. This one here would be kilojoules per kilogram. And this one would be kilojoules per kilogram seconds, or you could say kilowatts per kilogram, same thing. But good going, Aubrey, proud of you. So what we need to do is we need to write this as QL, whoops, QL dot. So that's what Aubrey said. That's what you said, wasn't it, Aubrey? QL dot?
Yes.
Yeah, absolutely right. So we're going to write that. So see, what you want here is big W dot, and what you want here is QH dot. Now let's keep reading. For those of you that just tuned in mentally, we're doing 535, and they want the smallest possible power motor required to operate this freezer. See, what they're asking is if this thing ran perfect, if it ran reversibly, no friction, no other bad, what we call irreversibilities, which we need to talk about. Here's where we need this these equations. Let me give you these equations. We're doing 535 but they don't call it efficiency. It's sort of the same thing, but they call it beta. And what beta is what you desire. It's always that over what costs you. They call it beta. They have another fancy name for it. They call it the coefficient of performance. Coefficient of performance. And in this book, they call it beta, but in older books, they call it a COP, coefficient of performance. So if you see that, you know what they're talking about. Now you have to ask yourself, what do we desire for our freezer? Well, I think what we desire, we want to keep our ice cream at -20. That's what we desire. See that -20 down there? We want to keep that ice cream at -20. And now to do that, you have to remove 2 kilowatts. That's what is that, 2 kilojoules per second from the freezer? Because if you don't, it'll warm up. If you unplug that freezer, you will no longer be removing the 2 kilowatts from the ice cream. It'll slowly warm up, it'll melt. So that's what you want. So here what you want is the 2 kilowatts. And now the cost, that's that W dot. But the thing is, we don't know what that is. We don't know what it is. That's what they're asking, I think. Let me read this. 335, 35. Heat must be blah, blah, blah. What's the smallest power? Yeah. See, this is what they're asking. We'll put a little mystery cloud around it. They want the smallest power if the thing ran perfectly. And here's how we're going to do it. There's 2 equations. This is your actual. Can you read my writing? Let me see if I can spell actual correctly. That's your actual beta. But there's another beta, and it's the reversible beta, or you could call it the maximum possible would be another name for it. There's different names for it. They call it the Carnot beta, the reversible beta, beta with no bad things happening. The thing is running perfectly, and it's based on your absolute temperatures. See here, let me write this. This could be written as the QL dot over the QH dot minus the QL dot. We'll put some numbers in here and that'll make more sense here in a little bit. But see, this here is based on the Kelvin temperatures. What you have is the TL in Kelvin or Rankine divided by your TH minus TL. Okay, we can do that. The only thing is it's got to be in Kelvin. Now, what is the temperature, the low temperature in Kelvin? Well, it's 253.15 Kelvin, isn't it? And what is the difference in temperatures in Kelvin? Well, it'd be 40 Kelvin, because the difference in temperatures in Celsius is 40, and the difference in Kelvin would be the same. Do I need to explain how come the difference in temperatures in Kelvin is 40? I'll write it out for you if anybody wants me to. Nobody asked. I guess you're okay. See, the difference in temperature is 40. From minus 20 to 20 is 40. But it's a difference in Celsius is the same as a difference in Kelvin. Do I need to write that out? I guess not. Don't be shy. Okay. Well, we can get this, guys. Look here. I got a calculator. I can figure out what that is. Now, I'll tell you something about beta. Beta is always bigger than 1. Eta, you know, for the efficiency, that's always less than 1. But beta is always bigger than 1. Okay, let me do that. 253.15 divided by 40. Did you get 6.33? We'll round it off. So that's the maximum possible beta that you can get. And that will give you the smallest possible power input that you need if the thing ran perfectly. So what we're going to do is we're going to set this equal to 6.33. Here, let me write it out better for you. What we're doing is we're saying beta actual is equal to beta maximum. That'll give us the best possible freezer that money could buy. And we just figured out what this is. It's 6.33. So we're going to take the actual, see the actual, and we're going to set it to 6.33. The thing is, we know what this is. We know. I think it was Aubrey that helped us on that. Let me see. Yeah, I think it was Aubrey that figured out that 2 kilowatts was a QL, big QL dot. I think that was Aubrey. And so look, you have a lovely equation here, and you can solve for this QH dot. Do we need to know that? What are we supposed to do in this problem? Let me read it. Let's see. What is theoretically the smallest power? Yeah, we'll get that. Okay, we'll get it. But right now, you are going to solve this equation for the QH dot, and I'm going to shut up for a minute and a half. On your mark. See that equation there? We know everything except the QH dot. Go ahead and get it. Here, I'll write it down here. I did that wrong. There. Well, I solved that, and I got an answer for QH dot. And I'm going to go to one of my wonderful students here. Hey, Stuart, we're back on picking on Stuart. Stuart, do you have that yet?
I believe so.
What'd you get?
2.316.
That's exactly what I got, Stuart. So we think that this, by the way, that has a name. It's called the heat transfer rate. That's the name of it. We think it's 2.316 kilowatts. Now we can solve for the power, because these two are going in and they have to add up to what's coming out. So guess what this has got to be? It's got to be 0.316 kilowatts. Can you see that? And we better put these in brackets because it can sure get confusing, huh? I think that's what they wanted. Let me read it. Let's see. 535. What's the smallest possible power motor required? That's it. You got to have a 0.316 kilowatt. It's a minimum. You can have bigger than that, and you're fine. But now, how about that was Stuart? How about somebody else? I need to hear an on that. I need another to feel good about this. Anybody else get 0.316 when they solve this?
I did.
Yay, there's another one. Now, was that Aubrey?
Yep.
Yep, that was Aubrey. Good going. Now we could check this. It probably wouldn't hurt anything to check it. Here. This is called checking our work. We're going to find the actual coefficient of performance by taking the QL dot and dividing by the W dot. Well, what is the QL dot? Well, that's 2. And what is the W dot? Well, that's 0.316. Okay, do that on your calculators and tell me what you get. 2.316. Boy, Jove, you get 6.33. Well, that's what the coefficient of performance is. It's 6.33. We checked our work. Anybody else have a comment or question before we go to the heat pump cycle? All right, well, if nobody has anything, we're going to go to the heat pump cycle now. I'm going to erase all this if you're happy. When you do these kind of problems, I want you to draw a cycle schematic. That's what this is. It's a cycle schematic. And for power cycles, it goes around clockwise. And for refrigeration cycles, it goes around counterclockwise. So let me make a little room here. And we're going to do a heat pump. Now, you all know what refrigeration cycles do. They cool off your car or your house or your ice cream or your hot dogs. But what does a heat pump do? Now, right now we're studying the heat pump cycle. And what it does is it keeps your house warm in the winter time. You don't want to make something cold. You want to warm up your house in the winter time, and you have a heat pump. Now, I don't have a heat pump at my house. I wish I did. They're very efficient. But I have a furnace. My house has a natural gas. It burns natural gas, and it keeps the house warm in the winter. But the way the schematic works is it goes counterclockwise, just like the refrigeration cycle. Round and round she goes. And it has a low temperature. And it has you might have little letters or big letters. And you might have big letters with dots on them. And see, this is your power input. Well, there's your schematic. You have a high temperature, you have a low temperature, you have heat transfers from the low temperature. Now you got to understand something. Mother Nature doesn't like it for you to transfer heat from low temperature and then have a heat transfer to a high temperature. Mother Nature doesn't like that. Mother Nature wants to transfer heat from hot to cold, not from cold to hot. If you go out in the wintertime and you're real cold and you come in and shake hands with somebody that has a nice warm hand, which way is the heat transfer? Well, it's from the warm hand to the cold hand. The cold hand will get warmer, but the warm hand will get colder. See, that's the way heat transfer always occurs in Mother Nature. It doesn't do this. It doesn't take energy from the cold and give it to the hot. It does it the other way. But you can do this, but you got to pay for it. See, you have to pay a bill to PSO at the end of the month for the electricity to do that on your freezer. You can keep your ice cream cold, but it's going to cost you because it's plugged in and it's using power from the power company. The schematic for the heat pump is identical to the schematic for the refrigeration cycle. There's no difference whatsoever. The difference is the purpose of a heat pump. The purpose is this heat transfer here, because this is going to your house. Here, we'll put a little roof on it. There we go. How about a window right there? Put a little door right here. There's a door and there's a window. See, the purpose of a refrigeration cycle is to keep your ice cream cold. But the purpose of a heat pump cycle is to warm up your house in the winter. Now, the symbol for it in your book, I think they use a beta prime for the coefficient of performance for a heat pump. And see, what it is what you desire. This is what you desire. And you divide it by what you have to pay for. This is what you have to pay for. But according to the first law of thermodynamics, that W dot is just the difference of those two. These have to add up. These two have to add up to that to obey the first law of thermodynamics. Now, this is your actual coefficient of performance of your heat pump. That's your actual. But see, you can have a maximum possible coefficient of performance. See, in the old days, they call it COP. And what it is TH in Rankine or Kelvin. And again, now they have these equations in your book. Let me see if I can find them here. I'm going to see if I can find these equations. I'm looking for these equations. Heat pump. Well, again, they have it in disguise there. But I do see this equation right here on page 172. And the way they did this one in your book is they didn't write it like this. They wrote this as, here's how they wrote it in your book. They didn't use dots over them. On page 172, this one, the book writes it as QH. See, they don't have any dots, but it's okay. They could have written it with little letters. And this just means the work done by your heat pump. HP stands for heat pump. And see that work done would be equal to the difference of these without the dots on. Hopefully you're not confused. If I were you, I'd write down these equations I'm giving you. Now we're going to do a problem. This is problem, we're going to do 533. I think that's the one I want to do. Yeah, that's the one I want to do. Okay, well, let's label this schematic. This is your heat pump schematic. And let's read it. Let's see, 533. A heat pump is used to heat a house during the winter. The house is to be maintained at 20 degrees Celsius. Well, that's what this is. Gee, I can't read my own writing. What's that? Oh, that's a doorway. That's what it is. And that's a window. Got confused there. This is 20 degrees Celsius. 20 degrees Celsius. Okay, keep reading. Ambient temperature outside is -10. Oh, it's cold. It's a cold February in Oklahoma, and we have a -10 degrees Celsius. When the ambient temperature outside drops to -10, the rate at which heat is lost from the house is estimated to be 25 kilowatts. Well, you see what's happening is there's a transfer of heat out of 25 kilowatts. And what you got to have is 25 kilowatts coming in from your heat pump if you want to keep that at 20 degrees. Because if this is less than 25, this will slowly cool off. See, this is radiating out into space and heating up the environment. And you want to keep it at 20. Because see, it's cold out here. The air out here is at -10. It's February. Okay, so we got that QH. Look here, let's circle it. Look here, we know what this is. And we know what this is. Hey, we know all of these too. We know what TH is. The only catch is we got to put these in Rankine. Look at all the stuff we know. But we need this. We need these in Rankine. Now, no, not Rankine. Kelvin. This here will be 263, won't it? And this will be 293. I think so. So this here is going to be. It's going to be 293 over what? Over what? Now I want to see if anybody's awake out there. I'm going to go to one of my wonderful students. I'm always picking on Stuart. Stuart, what do I put right here for the difference in these temperatures? What do I put right here? Yeah, I like it. Good going, Stuart. And now we're going to get this coefficient of performance. Here we go. See, Stuart's awake. Did anybody get 9.77 blah, blah, blah?
That's what I got.
Yay! Now, guys, that's the maximum possible. I'm not sure we're going to get that. Let me read this problem again and see what the heck we're supposed to do here. Oh, they want the minimum power required to drive the heat pump. So what we're going to do is we're going to set these equal. We're going to set these equal and we're going to solve it. I think we can do that. All right, here goes. What did we say this QH dot was? 25. All right. So what you got here is 25 kilowatts divided by 25 kilowatts minus QL dot equals 9.772. Well, we're going to assume this thing's running perfect and see that way we can solve for the QL dot. I think that's what we're supposed to do. Yeah. Okay, I'm going to shut up again here for a minute and a half. And I want to see, can you read my writing? Maybe. Maybe you can. I want to see if you can find this QL dot. It has a name. It's called the heat transfer rate from the low temperature. It's from the environment, which is February cold air. All right, go for it. Solve that, and we'll see what you get. Well, let me find one of my wonderful students here. Spencer, do you have this QL dot thing figured out yet?
I got 22.44 kilowatts.
That's what I got. I got 22.44 kilowatts. Now let me write it down here. This is 22.44 kilowatts, and this is 25 kilowatts. So we can get this. You just subtract. I can't quite do that in my head. 22, it'd be 2.56 maybe. Yeah, pretty close. I'm getting the power input required is 2.56 maybe. Did I do that right? Kilowatts. See, if 22 comes in here and 2.56 comes in here, and you add those up, well, then you get 25 coming out here. That's an expression of the first law of thermodynamics. The first law of thermodynamics for a cycle, in fact, this was the way the first law was first written down. Is this: the sum of all the Q's has to equal the sum of all the W's. And so see, you have a 22.44, it's going in, so that'd be positive. And you got a 25 going out, so that'd be negative. So that'd give you a negative 2.56. And the total work it's really a negative 2.56 because the environment's doing work. It's not positive work, it's a compressor, and compressors do negative work. I hope you're not confused, but I think that works. Sometimes the book is fancy and they'll write it like this. Or they could put dots over it. Doesn't matter. But the book will write this. This is the sum of, or the integration of, all of the heat transfers for your cycle. This little circle here on your integral, It's their secret symbol that denotes a cycle. So yay, we just did a heat pump. And now here's the interesting thing about heat pumps. You got to pay for this 2.56 kilowatts. You get a bill at the end of the month, or your landlord does. Somebody has to pay it. But this is free. This heat transfer here is free. And what they do is on the expensive heat pumps, they use the instead of they using the atmosphere, they use they dig down and they have their coils down there. The evaporation coils are down there in the ground. Would those be evaporation coils? Now let me think. I'm getting confused now. And see the ground. If you dig down, I don't know, about 4 foot, and measure the temperature down there, 4 foot down in the ground, it pretty much stays the same all year round. Isn't that interesting? So the air might be -10, the atmosphere in February, but down there in the ground, that would be warmer. Oh yeah, it's warmer down there. And so you can save some money with a heat pump on your heat bill. Do they have a heat pump description here? Let me see. On chapter 5. I'll have to look and see. Well, I tell you what, it's time for our little 10-minute break, guys. So here's our plan. Before the break, though, here let me summarize it and write all these equations out for you. How would that be? They're all in your book, but I'll write them out for you. If I can remember them all. Okay. Now this is for the power cycle. The power cycle, that's a Greek letter eta. And there's two different equations. And this one goes and this one goes now for the refrigeration cycle. It goes like this. Now that's the refrigeration cycle. But they use a Greek letter beta. That would be the actual, but see the maximum possible is in Kelvin or Rankine. Now for a heat pump, they use a beta, but they put a prime on it. It's beta prime. And they have an actual, and it's equal to this here. And this one here, beta prime, the maximum possible coefficient of performance. There you go. There's all your equations. I hope that makes some sense to you. And what we're going to do next after our break is we're going to study the Carnot cycle. It's a type of power cycle like one of these. Only these will definitely be equal because the Carnot cycle is a perfect cycle, no friction, no irreversibilities. We have a 10-minute break. When my big hand's on the floor, we'll be back. So go stretch for 10 minutes, and we'll do a Carnot cycle when we get back. Go take a break. You need a break. Well, welcome back. I think it's about that time. Did you copy all that down? That's good stuff there. Does anybody want to say anything about anything? I'm listening. Nobody wants to say anything. Well, I need the space, so let me erase all this good stuff. Here goes. Here's your last chance to say anything. Nobody said anything. Okay. Now what we're going to do is we're going to do the Carnot cycle. And it'd be nice to know what a Carnot cycle is. The Carnot cycle has two isotherms. And two adiabats. Now, I've told you about adiabats, but I don't know if you remembered. I don't know if you remembered about the adiabats. Let me go to my friend. We'll go to Parker. We'll pick on Parker. Parker, I told you guys what an adiabat was. Do you remember what it was? What's an adiabat? Earth calling Parker. Earth calling Parker. He's not back from the break yet. Oh, there he is.
Heat transfer is 0.
That's it. He's got it. He's got it. What an adiabat is the heat transfer is 0. Now, what an isotherm is the change in temperature between going from one state to another is 0. In other words, you keep the same temperature. So that's what a Carnot cycle is. But there's one added little thing, and that is a Carnot cycle is reversible. Every process is reversible, which we really haven't discussed, but it's like the perfect process. There's no friction, for example. See, friction kind of messes things up. There's a number of things that that cause what we call irreversibility. There's a whole list in your chapter. Let me see if I can find that. There's a whole list of things that cause irreversibility. Wonder if we could find that. Yeah, there they are. Page 153, it says factors that render processes irreversible. Well, what do they mean by irreversible? Well, it means that you can't get back to the way you were. I think aging is like that. You get old and you're just not the way you were when you were a teenager, okay? I'm sorry, but that's life. If you want to see a process that's irreversible, take an egg out of your refrigerator and drop it on the kitchen floor. And it splatters and the yolk breaks and you got yourself a busted shell and the egg all over. You're not going to get that egg back inside that shell the way it was. It's irreversible. Many processes in real life are irreversible. But there's a number of things that can cause irreversibility. They're in your book on page 153, 153, 154. And you guys could read that stuff. That'd be good. But Carnot cycles are pretend cycles. There are no Carnot real-life engines. Now, later when we study things like diesel engines, there are diesel engines in the real world. Gasoline engines, they're a real engine. There are gasoline engines, and et cetera, et cetera. But there are no Carnot, actual physical Carnot engines. It's a theoretical thing. A lot of things are theoretical, and sometimes you study them first and then the real things later. But what we're going to do is a Carnot cycle problem. It's problem 549. It's in your book, and we're going to solve it. It's on page P43 in my book. It's dealing with air. It's a Carnot cycle. So it's a heat engine or a power cycle, and let's just do the cycle schematic that we've learned for it. And I wonder, do they use big letters? Nope. You know what? It looks like they're using little letters. So they're going to go little QH. And this would be TL here. And this would be little QL. And this would be little W. And we're dealing with air. It goes in a cycle, Carnot cycle, PV diagram. We'll draw that in a minute. But the high and low temperatures are 600 and 300. Well, let me write that down. 600 K and 300 K. We'll write that down. The heat added at the high temperature is 250 kilojoules per kilogram. Well, that's this here. This is 250 kilojoules per kilogram. That's little QH. and the lowest pressure is 75 kilopascals. Well, I don't know where to put that on this sketch here, but we will on our PV diagram. But now let's go ahead and do that efficiency stuff. Now there's an actual efficiency and a maximum possible efficiency. They're going to be equal, do you understand? Because it's a Carnot cycle. And the Carnot cycle has the maximum possible efficiency because it doesn't have any irreversibilities. Now the actual is this W over the 250. Yeah, but we don't know what the W is yet. Now the maximum possible, you know what that is? That's the TH minus TL over TH. We just had those equations on the board here just a minute ago, and I erased them. But see, we know all of these. We know what TH is and TL. Yeah. So that's 600 minus 300 over 600. Hey guys, I'm getting 0.5. How about you? I'm getting 0.5. So we're doing great. Well, if this is equal to 0.5, see, they're equal. If you have a Carnot cycle, the actual is equal to the maximum. So I can figure out what this little W is. If this is 0.5, that has to be 125, doesn't it? See it? 125 kilojoules per kilogram. And so the QL would have to be, well, it'd have to be 125 because these have to add up. If you have 250 coming in and 125 going out, well, then you have to have 125 going out. So we know a lot of stuff already. Okay, great. Any questions so far? Now, I hope you wrote this down because I'm going to have to erase this to make room. And then we're going to do the PV diagram. Okay, well, if you think you got all that, I'm going to erase it. We know it's Wednesday, June 24th, don't we? We don't need any of this stuff. Let me just erase everything. Okay. All right, well, let's do our PV diagram. All right, PV diagram. Now, we don't want a vapor dome. We're dealing with air. So you don't have a vapor dome with air. It's not going to liquefy. And now, to be perfectly honest with you, if you got air cold enough and you compressed it enough, even air will liquefy. Have you ever heard of liquefied air? It can happen. But we're not going to do that, not with these temperatures. But what are our temperatures? I got lost. By the way, we're doing problem 549. And the temperatures are 600 and 300 K. Well, that's kind of in the ballpark of room temperature or a lot hotter. We're not going to liquefy. So what you'll have there is isotherms. And you know how those go. They go like that. And this is 600 and 300. And then a Carnot cycle, remember, is a 2 isotherm. So here, we'll do an isotherm here. There's state 1. There's state 2. There's state 3. And here's state 4. State 4. And there's your process from 3 to 4. And then 4 goes back up to 1, like that. And you're back where you started. See, you've got a cycle. You go from 1 to 2 on the isotherm. 2 to 3 is an adiabat. There's no heat transfer from 2 to 3. 3 to 4 is an isotherm, and 4 back to 1 is an adiabat. No heat transfer. Now what we're going to do is we're going to make a table, of a property table with energy transfers in it. And it's going to go like this. We'll have P, V, T, delta U, Q, and W. Now what we're going to put in these values, we're going to put in the initial amounts on those properties there. We don't know the pressure at state 1, and we don't know the pressure at state 2, but they did give us the pressure at state 3. They said, if you'll read the problem, we're doing problem 549, they said the lowest pressure in the cycle is 75 kilopascal. So at the beginning of the process from 3 to 4, we're going to put the initial amounts here. The process at state 3 is 75 kilopascals. Now the temperatures, we know what the temperatures are at state 1. At state 1, it's 600 K. And at state 2, it's 600 K. State 3 is 300 K. And state 4 is 300 K. We know all those. Now we also know what the heat transfer is. If you'll read this, the heat added at the high temperature is 250. They gave us that. And on our schematic, we figured out that the heat transfer at the low temperature was 125. But see, it was going out, so it's a negative 125. I don't know if that made any sense to you. Here, let me draw them on here. There's a heat transfer here from 1 to 2. here it is, of 250 kilojoules per kilogram. And there's a heat transfer out here of 125 kilojoules per kilogram. The amount's 125. The minus means it's going out. The amount is 250. There's a plus there. That means it's going in. There is no heat transfers on these adiabats. On both of these, the Q is 0 because that's what Carnot cycles are. They have two adiabats. Now, we've got a P1 or P3 and we have T3. Look here. P3 V3 is equal to RT3 because we're dealing with air, remember? And if you know P3, and you know R, you can look it up, and you know T3, we can solve for V3. So we're going to take out a minute and a half. I'm going to shut up, and I want you to find V3 for me, students. And then I'll ask one of my better students, some of the sharpest ones in the pencil drawer there in a minute, what the answer is. So go for it. See if you can get it. Find the specific volume at state 3. Go for it. Well, let me pick on one of my excellent students here. Bear, I'm picking on Bear. Bear, do you have V3 yet? Unmute, Bear, and tell me what you got for V3.
I don't have that just quite yet.
Oh, take your time. There's no hurry.
Uh, 33.25.
Now that's Bear talking, right? Was that Bear? There was somebody just said something.
That was Bear.
What'd you get, Bear? For V3?
I got 33.257.
Something bad happened, Bear. Let me write it out for you. I think you're wrong here. But see, this here is 75. And there's your V3. This is 0.287. And this is 300. And when you solve that, I got 1.148. Do it again. Now, did anybody get that? If they did, say, uh-huh.
I got 1.148.
Yeah, good for you. Okay, well, good. Well, we made some progress. Now let's get some of these. Now, wait a minute. You know what? These here are going to be 0. How come? Now let me pick on one of my wonderful students here. Aubrey, how come those two heat transfers from 2 to 3 and from 4 to 1 are 0? How come those are 0, Aubrey?
I'm not sure.
I'll give you a hint. It's because these processes are, starts with A, Aubrey, just like your name. These processes,
Adiabatic?
that's it. That's it, by Jove. They are adiabats. They don't, see that Q is 0 there? They don't have any heat transfer because they're adiabats. 2 to 3 and 4 to 1 are adiabats. Good going. Now, I'll pick on another one of my wonderful students here. I'm always picking on Stuart. Stuart, do you see these delta U's from 1 to 2 and from 3 to 4? Those delta U's are 0. Stuart, how come those delta U's are 0 from 1 to 2 and 3 to 4? How come, Stuart?
Is it because it's isothermic?
Yeah, that's right. That's a pretty good answer. See, now Stuart knows that delta U is equal to C sub V delta T. Now, I'm going to ask Stuart something. What's the delta T going from 1 to 2, Stuart? What's the delta T?
0.
0. See, this here is 0. And so you have 0 on the right. So that makes your delta U 0. That's how come, and Stuart got it. It's the isotherms. Now we can get that little W there. Here's an equation for you. Let me make a little room here. Some room up there in the corner. I'm still picking on Stuart. Stuart, this is a very important formula. You see this formula right here? Stuart, it's got a name. What's the name of this formula? Unmute
Not sure,
Stuart.
just off the top of my head right now.
That's okay. You're here to learn. That, I'll give you a hint. That is probably the most important formula in the entire course. It starts with something that looks like this. Stuart, what do you think it is?
First law of thermodynamics.
By Jove, he's got it. It's the first law of thermodynamics. He's got it. Now the reason why it's this version, remember there's another version, another longer, we worked on it last Monday, I guess, or last Wednesday, I don't remember. We worked on the version for control volumes, but see, this is not a control volume. This is a piston cylinder. It says so. If you read problem 549, It says air in a piston cylinder. Well, that tips you off that you're dealing with a control mass. See, this is the control mass version of the first law. And look here, if you know delta U and you know Q, you can solve for W. One last thing here, Stuart. I know you can do this. If delta U, if you know that, and you know the little q, what's the little w, Stuart? Go for it. Little w is from 1 to 2. What do you think?
250.
I like it. I like it. Good going. Now I need to pick on somebody else because I'm always picking on Stuart. So we just did that. Now I'm going to pick on Spencer now. Spencer, this same equation should work going from 3 to 4. Look, we know what delta U is from 3 to 4. We know the Q from 3 to 4. So Spencer, I'll give you a big honking hint here, Spencer. This is going to be plus or minus 125, but which is it?
It's negative 125.
Good going, proud of you. You're absolutely right. Because if you do the algebra, if this is 0, and this is minus 125, and then you have a negative in the equation, this has to be a negative 125 to get the algebra to work. So look at all the progress we've made. Well, let's do this one here now. I just need some room here. See, our goal is to fill out this entire table of properties and energy transfers. That's our goal. And we made some progress. Look, we're coming along. Now, what we're going to talk about here is going from 2 to 3. Well, from 2 to 3, delta U from 2 to 3 is equal to C sub V delta T. Now, C sub V, if you look it up in the back of the book, I believe is 0.717 kilojoules per kilogram Kelvin. Let me pick on my wonderful student Spencer now. I'm going to talk to Spencer.
Yes.
Yeah, Spencer. What is delta T going from 2 to 3? Going from state 2 to state 3. What is delta T?
Negative 300 Kelvin.
Yeah, absolutely. Good going, Spencer. Now I want you to solve that and get this delta U from 2 to 3. This is the change in specific internal energy. That's a fancy name for it. Go for it. I'm going to do it. I'm getting a negative 215.1. How about you guys?
What I got.
Great. Now we can get the work per mass going from 2 to 3. And here's how we're going to do it. Now we know what this is. We just did it. It's negative 215.1. We got it. And we know what this is. It's 0 because it's an 80 bit. So you can solve for the work per mass from 2 to 3. And I'll give you a hint. It's either plus or minus. We'll bother Spencer one more time. Spencer, plus or minus 215.1 on that.
Positive 215.1.
Absolutely. Now here's how I think about it. When you're going from 2 to 3, that's expanding. See, the V's are getting bigger. Expansion work is always positive. So when we go from 3 to 4, that's compressing. So that's going to be negative. And from 4 to 1, that's compressing. The volume's getting smaller. So that the work, well, look, it is negative. We've already figured it out. From 3 to 4, it's negative. This one's going to be negative too. Now we're going to get this delta U from 4 to 1. I'm going to shut up for a minute. I want you to solve, and I'll pick on one of my wonderful students here. Let's see. Parker, can you figure out what the delta U is from 4 to 1, Parker?
Yeah.
What do you think?
Is it 215.1?
That's what I got. You know what? It's the same as this. It's the same numbers. But from 4 to 1, you're getting hotter. So it's the same equation. It's just that the delta T is not negative 300, it's plus 300. Hey, Parker, look at here. If you know 2 of these things and you know your first law, what's going to be the work per mass, Parker, for 4 to 1? What's it going to be?
Negative 215.1.
I think you're right. Good going. Hey, look at all the stuff we filled in. What are we going to do now, though? Here, let me help you with these, and we're going to fill those in. Now, going from 3 to 4. You know what? That's an isotherm. We have an ideal gas isotherm going from 3 to 4. Now, I've shown you this before. The work per mass going from 3 to 4 on an ideal gas isotherm is equal to Does anybody remember me showing you guys that? I derived it one time. I think it was a couple of sessions ago. I think I derived it in general. But if you have an ideal gas isotherm, it's a polytropic process with n equals to 1. Now watch this. P3V3 is equal to RT3, isn't it? Now let's circle the stuff we know. Do we know the work from 3 to 4? Yeah, look at here. Yeah, we got it. Do we know R and T3? Well, yeah, we know T3 and we know R. Do we know V3? Yeah. Hey, look at here, guys. We have a nice equation here now. And there's only one unknown. Here we'll put a little mystery cloud around it. Now I'm going to shut up for 2 minutes because you must know how to do this. And I want you to solve for V4. And if anybody doesn't remember this equation, just ask and I'll go back over it. But you've got 2 minutes to solve that, and I want to see if you guys can do it. On your mark. We are solving this equation right now. When I circle stuff, that means we know what it is. There's only one unknown. Okay, do it. Well, I'm having a little trouble getting it, but we're going to get it. Well, I seem to be having a lot of problems getting that. Maybe we should write it out carefully, because if I'm having problems, you probably are too. Okay, we think that the work per mass from 3 to 4 is negative 215.1 kilojoules per kilogram. And that's equal to R, which is 0.287 kilojoules per kilogram Kelvin, times T3, which is 300 K, times the natural log of V4 over V3, which is 1.148. Okay, now I'm going to do some algebra now. I'm going to take 215.1, and I'm going to divide by 0.287, divide by 300. And here's what I have in my calculator so far. And you might want to double check me and make sure I got that right. I think it's right. And then what I'm going to do is I'm going to take the anti-natural log of both sides, And if you do that, here's what my calculator says. And now I'm going to solve for V4. I wonder if I did that right. It's not the answer I got when I did this before. It's not what I got when I did it before.
Shouldn't that be minus 125 for the W?
Oh, that's where I'm goofing up. That's thank you. Was that Spencer?
That was Stewart.
That was Stuart. Stuart, we're going to give Stuart a big honking thank you point. I'm having trouble here. And the reason is because from 3 to 4, this should be a minus. I had the wrong number here, Stuart. It's minus 125, isn't it? Yeah. Good going. Thank you point there for Stuart. Proud of you. Okay, now I'm going to do this and do it right. Couldn't get the right answer and I couldn't figure out why. Why? This is wrong. But we're going to get it right. See, between us, we can do this stuff. With your help, we can do this stuff. Don't want that. That's wrong too. But we're going to get it now. Here goes. 125. Okay, and then what do? You take the anti-natural log, and then I think you multiply by 1.148. Yeah. Are you getting V4 equal to 0.2688 cubic meters per kilogram? Anybody getting that?
That's what I got.
Yay! Good going. Okay, now let's put it in here. It's 0.2688. Now what these are cubic meters per kilogram. Excellent. Now look at here, guys. If you know V4 and T4, you should be able to get P4. Because look, how does it go? P4 V4 is equal to RT4. Yeah. And see, we know R, we know T4, we know V4 now. We can get P4. Okay, I'm going to do that. I want you to find P4 now. We're finding P4. Look, we know V4. It's right here. We know T4. It's right here. We can find P4. Go for it. And I will pick on my good student, Parker. Parker, do you have the P4 yet?
Not yet.
Take your time. Take your time. How about Bear? We'll pick on Bear here. Bear, have you figured out P4 yet, Bear? Unmute and tell me what P4 is, Bear.
I have, not sure if it's right, but I got 325.15.
You know, that's dang close to what I got. I wonder why we're different. I'm getting 320.3 for P4. Do yours again. I'll write it out if you want me to, Bear. Here, let me write it out for you. P4 times V4. I wonder if I did that right. P4 times V4 is equal to R T. Plug that stuff in and see what you get.
Is the V4 0.2688?
Yeah, that's what I got.
Okay, that might be where I made a mistake. Well, one of those numbers looked like a 4 to me.
It's 0.2688. Now, when you solve that, I'm getting 320.3. And I'm listening for an uh-huh.
I got that.
Yeah, good. Well, we got 4 more boxes to do. And we have 9 minutes to do them in. And let me show you what you have to do to get those. In chapter, we're in chapter 5, I think. Yeah, we're at 5. There's some equations there in 5 that we're going to explain a whole lot better when we have a little more time. But I only have 9 minutes right now. And these equations are on page 160. And I just need a little room here. There's some room up here. And we're going to get these last 4 boxes. To do them, you need to be on page 160 in your book. And one of these equations goes like this. You wonder, well, where on earth did they get these equations? Well, that equation isn't going to help us any because we don't know. I read the wrong one. Yeah, there we go. Yeah, that equation will work for us. And then there's another equation. on page 161. Yeah. And that equation goes like this. We're going to explain these equations when we get a little more time. But right now, we don't have a little more time. Now, you got to be careful with these equations. They only work for ideal gas adiabats. Now, you could read the book and they'll explain why on page 160 and 161. And we'll explain much better when we get time. But see, we can use, say, let's take this equation here. Now, this is going from state 4 to state 1. See this adiabat right here from 4 to 1? I'm going to do it down here. I got a little room down here to work. And they're saying that you have 0 equals. Now what we're going to do is we're going to take out that constant out of the integration. And when you integrate dt over t, what you'll get is the natural log of the th over the tl, which is 600 over 300. Minus, plus r, which is 0.287, natural log. I'm doing this one here from 4 to 1. We're going from 4 to 1. And I don't know what V1 is, but I know what V4 is. It's 0.2688. This is a little bit ugly, I know. But there's your numbers, and we can solve that for V1. Now you use this equation here to solve for V2. Here, let me write it for you. That equation there, it's the same thing, only you're going from 2 to 3. So you're going from state 2 to 3. You're using that adiabat. This equation works for an ideal gas adiabat. When you pull out your constants, you'll have 0.171. And when you integrate dt over t, you'll have natural log of, but it's just the opposite. It's 300 over 600, because you're going from 300 to 600, from 2 to 3, plus r, and this will be V3, which we know what V3 is. It's 1.148 divided by V2. It's sort of like magic. You wonder, well, where did he get these equations? Oh, I'm going to explain them in time, but I only have 3 minutes left. Now you can solve these. You can see, you know, all the numbers except V1 and V2. And if you'll solve this equation here, I'm just going to tell you what the answer is. This answer is 0.04758. And I want you to do that to make sure that I did that right. And this answer here, that would be the answer here for V2. And it's we don't have time right now, but if you'll do that, it'll take you about 2 or 3 minutes to solve this and that. These are equations on page 160 and 161. There are equations for ideal gas adiabats. They only work Those equations that I just wrote are only work for ideal gas adiabats. Now, you know the first, or the ideal gas law, if you know V and T, you can get P. So let me just put the P's in there, and you should do this. If you do this, you'll get 3619.4. I'm running out of time, so I'm just going to tell you what they are, but you should check it. So to make sure that you know how to do this, 847.4. There, that's how you fill in the entire chart. And I showed you how to do it. Now let me show you this. If you add all these up, you know what you'll get? You'll get 125 kilojoules per kilogram. If you add all these up, guess what you'll get? You'll get 125 kilojoules per kilogram. Guess what? The sum of all the Q's in a cycle is equal to the sum of all the W's in a cycle. And the efficiency. Oh, gee, I have 1 minute left. The efficiency. Need a little room here. Right here. I'll write it. I got a little tinier bit of room right here. We did 549, but the efficiency, there's two kinds. There's the actual, and there's the maximum. They both give you the same thing. And for the actual, you get 125. That's the net work. That's the total of all the work is 125. And the 250 is the what you have to pay for. Remember, it's the cost. You always divide by the cost. And you have to pay for that. See, that 250, you have to burn some fuel. This is just warming up Oklahoma here. But this, you have to burn some fuel. It's 250, and you'll get 0.5. But we got 0.5 a long time ago, remember? Because we did it with the, can you read my writing? That's supposed to say actual. How do you spell actual? There you go. We did it a long time ago and got 0.5. Last chance for a comment or question. If I don't miss my guess, I think you guys have a test to work on. If you go to Blackboard, I think the test has become available, and the deadline is written on there for your test. I forget when it is, the deadline. I hate to tell you that because it's written down there, and I told you the wrong thing one time. I don't want to tell you the wrong thing, but I think it says Saturday night at midnight. Now, what is this? This is Wednesday? Oh, you got lots of time. I think there's also some homework that you need to work on. There's homework and a test. You got enough to do to keep you busy. But our time, it's sad, but our time is coming to an end. And here's your chance, your last chance to say anything to me. Go ahead, I'm listening. Well, okay. I'm going to say goodbye. And you guys work on your homework and your exam. And last call, 5, 4, 3, 2, 1. Goodbye, students.